October 2020, and we are back with another SecTalks Sydney live session. Welcome, everyone. This is our 61st session, or 42 in hex, if that makes sense more to you. And since lockdown, this is our 7th session. There will be two parts to this evening session. I will be your host for the first part, and Joshua, hopefully at some stage, will join me to host the second part. The second part, there will be our usual 60-minute CTF game. Now, what we are going to have in the first part, we will be having two presentations. Our first presenter will be from the winning team of the past month's 60 minutes CTF, and which is here with us, Jordan. And our second speaker, well, as you may guess, the internationally known security researcher, Dr. Peter Gottman, which is great to have him again. And he will be presenting on the topic, which I will get to that a bit later. Now, a quick few things. Please use the YouTube chat or the SecTalks Slack channel to ask your questions. We do also have our IRC channel available to you, which you can use to ask your questions. All these details will be shown to you throughout the presentation. Or if you just head to sectalks.org website, you can see the information around where you can find our IRC channel or how you can join the SecTalks Sydney Slack channel. I did check with our speakers. They are happy to take your questions during the talk. We're also going to have plenty time available to ask for Q&A at the end of the talk. Now, if you have ever experienced doing a live talk or presentation, you know that it is nothing more strange than presenting to a screen. So please use these chat channels to ask questions, your early feedbacks, and comments. But also at the same time, please, let's be civilized. This is not Twitch type TV to throw out all the trolls and questions. So without further ado, let me just bring up Jordan's screen here. Just quickly bye for Peter for now. So Jordan, he will be, well, talking about the CTF channel of the last month.
Yep.
Go ahead.
So thanks, Pedram. So last month we had 3 warm-up challenges, warm-up 1, 2, and 3. And then we had a harder challenge, not my modulus. So warm-up 1, we start off just given some 5 lines of text, whatever. I mean, anybody looking at this would kind of know that these look like hashes, fixed length, sort of all the same. So obviously the first thing we did was threw them into CrackStation, did the capture, and then out pops the flag. It's EBQSA, and that gave us warm-up 1. So then moving on to warm-up 2, we see 2 emojis, random order seemingly. Generally, when you see something that's like this, where there's just 2 different symbols, it's either Morse code or binary. So we tried Morse code. So just finding a replace with the emojis to the different strings, you can try the different combinations, and taking those, you can chuck them into CyberChef, and then unfortunately nothing from that. But then trying binary, just also finding and replacing with the ghost and the alien, you can copy this into CyberChef as well, and that will give you your other flag for warm-up 2. And then moving on to warm-up 3, we're just given this big block of text. So generally, like when you get something given like this, you want to kind of look for patterns, I guess. So looking at this, we can see that we have a lot of capital letters for the start of the people's names, and then sort of like filler redundant information. Favorite letter is, it's the same, it's repeated throughout here. And then something that seems important, like the actual favorite letter. So this one took us a little while to solve, but one of our members realized that if you can correlate the first letter of the name to the favorite letter, you can sort them. So the way we did that was over here. So just chucking it into Python. This line is a little bit complicated. I can assure you it didn't turn out like this, but this is the neat version. So all we do is we are running a regex over our big string given to us on CTFD. And that's just looking for a word, the first name, favorite letter is, and then capturing the actual favorite letter. And then we can split that up into a dictionary of the first letter of the first name and the favorite letter from all the matches in that string. And then we can go ahead and just sort that dictionary by the first letter of the first name. We tried sorting it by the favorite letter, but obviously that didn't turn out too well. And then so doing that, we can just cut this dictionary out, sorted one out, and then we are given that password for warm-up 3 and submit that to get the flag. And then, so now moving on to not my modulus, the harder challenge. This is the one that took us the longest. Like this took us the whole hour pretty much. There was a team that got it before us, but I think we were pretty close, hopefully. So we are given trying to decrypt a packet capture taken on our internal network. We know you can decrypt the data using the correct private key, but we simply have too many. Can you identify the correct private key? So downloading this file, we can extract it, and what it gives us is this keys archive and a PCAP. So opening the PCAP in Wireshark, which I have open already, it's just, you can see it's most likely, so TLS data. It's probably just encrypted HTTPS data. So in order to read the data, which is probably going to contain the flag, we need the private key. And then seemingly the private key is going to be in this keys folder. But the issue is there's probably like, I think 500 something keys in here, way too many to go through by hand. So going back, we can look at the title of the challenge and realize that it's a hint. So in the private key files, there'll be a modulus, and in Wireshark, the modulus is required to set up the secure channel, the encrypted channel. So we can find that. I'm not too sure actually how I did that, but the gist of it is you kind of go into these fields and somewhere in one of these drop downs, you'll be able to find the modulus. But yeah, not too sure where I got that from at the moment. So after you get the modulus, we tried a bunch of things. We tried to input it over here. So like we tried, before we got the modulus, actually, we tried to input all the private keys at once, and we thought Wireshark would just automatically decode it for us and we could find the decrypted data. But we realized that we would have to find the actual file after a while. So if you come down to your Wireshark preferences, which you can access just by going to preferences, protocols, we want to go to the TLS section, which is down here somewhere. And then there's an RSA keys list section. So if you click edit, it'll give you space to add a key. And this is where I thought I could add them all at once by going here and then editing this file and just pasting the path in for all of them, but that didn't work out. So yeah, once you find the key, you are able to just select it and put it here, and then it will decrypt it for you. So the trick to finding the key is we're going to use OpenSSL. So this over here is the hex encoding of the modulus. So we found that from Wireshark and put it into the format required by OpenSSL. And so what we do is we just loop through all of the files in the keys list, which is all these ones. And then on each file, we're just going to examine that file with OpenSSL and get the information printed out to standard out, which will contain the modulus. And then we're just grepping for the modulus. And we're printing the name of the file before each one. So that when we get a match, we know which file it is, rather than just matching the modulus. So if you run that, you'll run through a bunch of them really quickly, and we're going to catch it with Control-C when we see it. So there it is. We can see we got a match for our modulus under this key file. So all we need to do now is get the path to this file my hacky way, and then just chuck it into Wireshark, basically. Paste it over here. So clicking OK, OK. So I did this like 20 minutes before I found the flag, and then I didn't realize that you have to look down here at the bottom. There's a decrypted TLS tab. I just thought it would automatically decrypt it and you'd see plain text, but no, you have to come down here and click this decrypted TLS tab. And so looking at all the sent data, we can see that under this application data packet, we can see the flag here. So yeah, you just grab that 24/7 CTF and some numbers, hex, and then chuck that into CTFD, and then we got our flag. And that took us about an hour.
Yeah, beautiful.
Thanks.
And I guess you also have the challenge for tonight, the main one that we are going to present. Well, I hope Joshua join us at the right time. Now, let me ask, how many people do you actively have in your team? I think you're pretty much like top on the leaderboard here with 2055.
So we have a Macquarie Society, and we got a bunch of people to join from there. And then when we were running in-person sessions, we got mixed up with another team as well. So I don't think they actively compete, but they're just stuck in our team now. So we're a big team.
There we go. Well, challenge is on for the other teams. Thanks again, Jordan. Hopefully we will bring you back at the second part. Now, going back to our main speaker, we just quickly introduce Dr. Peter Gottman. He's a security researcher in the Department of the Computer Science at the University of Auckland, working on the design and analysis of cryptography, security architecture, security usability, and embedded system security. And some of you may have remembered, we had Peter last year, what was it, around August, I think. You fly all the way to Sydney to give us an interesting talk on automotive security, if I remember correctly. Yeah. And but now we have him all the way from Auckland joining us. And thanks again, Peter. I know it's around 8 p.m. over there to take your time. So Peter will be here to talk about software security.
Anyway, so it's fine.
What's that, sorry?
I usually work evenings anyway, so it's normal working hours for me.
That's great. So Peter will be talking about software security in the presence of fault. And software security is usually concerned with the issues like buffer overflow, SQLi, integer overflow, blah, blah, blah. But what is rarely is considered, and this is pretty much what I'm excited about to hear, is the behavior in the presence of fault, which typically may be overlooked. So we have Peter here to talk a little bit more about this to us and see what we can expect. Thanks, Peter. The stage is yours.
Thank you. Okay, so, let me just see. I'll have to flip windows, I think. So what I'll be talking about is, as the introduction said, software security in the presence of faults. So faults in the sense of crypto fault attacks have been known for quite some time, and these are mostly of concern to cryptographers. So basically, if you can do get a fault during a crypto communication, then an attacker can recover encryption keys. And this has been studied to death by academics since then. In particular, elliptic curve cryptography is particularly susceptible to faults. So if you get a fault with the in-memory key, it leaks the private key. If you get a fault in the elliptic curve computation, it leaks the private key. If you get a fault in the random number generation, it leaks the private key. You can probably see a pattern emerging here. So the general idea behind these faults attacks on ECCs is you move the computation from the secure curve to another curve by causing, say, a bit fault that is then inevitably weaker than the secure one, or you produce a faulty point in the original curve. So you're basically moving it from a secure to an insecure space. RSA also has issues with faults, but it's nowhere near as bad as ECC. In the RSA computation, if you sign the exact same message twice and you get a standard signature and a faulty signature, then that's a problem. But this essentially never occurs. None of the standard crypto protocols have this problem. So ECC, in contrast, has entire catalogs of fault problems which don't require these duplicate signatures. And there's a bunch of other mechanisms like PSK's pre-shared keys, so basically symmetric key-based stuff. Doesn't have any issues. Authentication doesn't use signatures. They're built around hash-based mechanisms, and so they don't have that problem. Symmetric crypto, again, doesn't have random fault issues. There are attacks that require injection of specific attacker-controlled faults, but not just random faults in random locations. And it's the same as with RSA. They require encryption of the same data 2 or more times. And again, as with RSA, that typically doesn't happen because you don't encrypt exactly the same data with the same initialization vectors. There is a mode called GCM mode, which is very trendy, which fails catastrophically on an IV fault. So there's a cryptographic value called the initialization vector, which is part of this encryption process. If you get a fault with that, the whole mode fails catastrophically. So the downside of this is the two trendiest encryption modes, which are elliptic curve crypto and GCM, are also the most brittle in the presence of faults. And in the worst case, if you get a fault on the random number generation, you lose everything in one go. You lose the elliptic curve private key, you lose confidentiality, and you lose integrity protection. The most robust integrity mechanisms are probably RSA and a different integrity mode called HMAC, but they're not fashionable, so no one wants to use those. So the way you carry out one of these fault attacks is you wait. It's an entirely passive attack. You don't have to do anything except watch network traffic or something similar and wait for a bit to be out of place. So some of the causes of these faults are just standard electrical glitches, over voltages, under voltages, spikes, clock glitches, noise, any kind of noise or glitch or anything like that. You've got thermal issues. And a very odd one that most people don't consider is radiation. And radiation introduces electrical glitches and can also change circuit operations both temporarily and permanently. So typically randomly appearing faults will do a bit flip, a 0 becomes a 1, 1 becomes a 0. Rather unlikely type of fault is one during computation because most CPUs have error detection and all sorts of error correction and recovery circuitry in the CPU core. Some go to extreme levels to do this. So typically that's very, very unlikely. And what you basically never find is non-random attacker-controlled faults. Simply because an attacker who can disassemble your device and sit there injecting faults can do whatever they want with it anyway, and they're not going to bother with something simple like injecting faults. And then you've got a problem about theory versus reality. So research results are often very difficult to apply. Here's a typical set of research results, and the ones that you're actually worried about, which is you've got no control over the timing or location, doesn't really occur because researchers assume you can magically say we're going to flip this exact bit from a 1 to a 0, whereas in practice random faults don't do that. And there's also a lack of understanding by cryptographers. I'll skip through these slides, but basically the problem is that if you've got things like SCADA and embedded implementers who are running equipment in harsh environments where you really will get faults, they don't really talk to each other. The cryptographers say we've got these amazing theoretical designs that don't have problems. Why isn't anyone using them? And the implementers are saying, well, this stuff doesn't actually do what we want, so we'll have to come up with our own way of doing it, which is often not cryptographically sound. There have been a few studies published on this security problems. So again, it sounds like a relatively high number, but it's, faults aren't that common. So, but when the faults do occur, a scary percentage of them do actually result in security problems. In fault-aware embedded systems, code corruption isn't, which is what these figures are for, isn't normally a problem because either the code executes directly out of non-volatile memory, and there's an example there of an embedded controller, and it just executes straight out of flash, or if the code's in RAM, the real-time operating system will have a monitor process that sits there checksumming the code segment, and it'll restart the system if there's a code error. So code corruption isn't normally a problem, it's data corruption you've got to worry about. So, okay, why am I so worried about radiation-induced faults? Certainly they do occur in the wild, but there are some situations where they occur a lot more than in others. And that's, for example, when you're using crypto to monitor nuclear materials. So it's used by the UN to check compliance with non-proliferation treaties. And they will have, for example, devices monitoring fuel storage ponds to make sure that fuel rods don't go missing, particularly in breeder reactors where you're breeding plutonium. You don't want fuel rods to start going missing there. So what they'll do is take a snapshot of that and digitally sign this image and send it out to say nothing's changed. Monitor of reactor refueling. Again, you want to make sure that fuel rods don't get diverted and used for purposes they shouldn't be. Monitoring of waste management. Again, you want to monitor what's leaving this facility, and if there's anything like plutonium or whatever leaving, you want to make sure that it goes to a designated disposal site, not to who knows where. So, those are, I've called them high radiation environments. They're not really that high radiation in the sense that humans don't have to work there. And so in this case, you get this interesting definition of tamper discouraging crypto. So it's you're welcome to tamper with it, but the radiation will kill you. So it discourages anyone from going in there and trying to tamper with it. So the thing with this is it's not specific to reactors. I mean, reactors are cases where it does occur a lot more than other places, but in harsh environments in general can experience faults. And there's a whole bunch of standards on this: railway applications, gas detection systems, medical systems, nuclear power plants, functional safety, which is in all sorts of automotive, aircraft, things like that, industrial control, road vehicles, and so on and so forth. This is just a sample of some of the standards that cover dealing with faults in computer systems. So there have been failures due to radiation outside of use in reactors. One of the most best known, at least among people who study this kind of stuff, was in the ACQ supercomputer at Los Alamos, and this was some years ago. It was built with DEC Alpha CPUs, and what they did is they had error detection but not error correction on the level 3 cache, because it was a speed critical case and there wasn't any capability for adding error correction without slowing it down too much. So the standard data RAM itself has ECC, but the cache RAM does not have ECC. And what happens was that it detected the faults via parity, but there was nothing to respond to that. So they weren't corrected. There was no scrubbing, anything like that. And as a result, the node crashed. IBM did it slightly differently. So if there's an error in cache, it's treated as a cache miss and the cache gets reloaded. Whereas with this one, there's a software notification and the software notification was ignored. And they suspected cosmic rays because it's at very high altitude, 2,300 meters. And the cosmic radiation there is 6 times as intense as it is at sea level. And avionics computers, it's even worse. It's 150 times as intense as it is at sea level. And so typically a node in this supercomputer experiences a fatal soft error once in 50 years. With a 500 node cluster, they were hitting one once every 1.5 hours. And they just happened to have a neutron science center at Los Alamos, along with a bunch of other radiation sources. And they used this to confirm it was radiation related. And so they dealt with it by basically not ignoring the soft fault. So they scrubbed the cache RAM and did checkpoints and a bunch of other stuff to deal with this in software. So with modern CPUs, you can get all sorts of unexpected failures. There was some testing done a while back with a Pentium 3 CPU and a K7 CPU. Again, this was done a couple of years ago. And they exposed it to a gamma radiation source. And they expected, with the high complexity of these CPUs, that there would be a fault in the CPU. In fact, the CPUs kept running. The fan controller failed because it had a PWM fan control chip, and that died long before the CPU was actually affected. And they found, for the testing, they actually shielded all the components except the CPU. And the CPU was raised above the shield directly into this beam of gamma rays from a cobalt-60 source. What actually happened was the gamma rays hit the CPU and scattered down into the components that were supposedly shielded. And so they destroyed motherboards, they destroyed video cards, all sorts of stuff, rather than the CPU that they were actually trying to test. And one interesting thing they found out was the Pentium 3 took 100 times the radiation dose of the K7, leading to the conclusion that these things are practically radiation-hardened devices. This may be because of Intel's bad experience with alpha particle contamination in the 1970s. So they were basically, their main product at that time was 16K DRAMs, and they had problems with the packaging, which contained alpha particles or radiation sources that emitted alpha particles. And so they're getting failures in their DRAM, and it was a kind of a bet the company thing, can we fix this? And because of that bad experience, they may be a bit more nervous about radiation than others. If you look at this diagram, which was from a slightly more recent set of tests, this was on the increasing radiation hardness of these various different Intel and AMD processors. So you can see in the mid-90s, there were a few K-rads, it's what you'd find in a reactor environment. You wouldn't want to stand around there too long, but it's relatively low. And at some point, they're going into 500 K-rads and then mega-rads, which is a staggering amount of radiation. So these things are military-grade radiation-hard devices, except that they're standard desktop CPUs from many years ago. Yeah, so the ITAR level, which was the level at which something is regarded as a military-grade radiation-hardened device, is 500 K-rads. And these things were taken from 1 to 17 megarads. So all of them were essentially, this vintage budget desktop CPU was a military radiation-hardened device as far as export controls were concerned, because they put so much effort into radiation hardening these things. IBM Power do the same thing for their servers. You don't want a mainframe to go down because of radiation-based faults. So they've got massive amounts of protection circuitry, and they actually hit it with proton beams to make sure that it would keep running in the presence of this radiation. Spark CPU, the same thing. And they've got lots of error detection, lots of error recovery, and so on. So an intense neutron bombardment, which is pretty much running the thing, close to the core of a reactor. Virtually all errors except 2% were recovered from, or simply all vanished. And so you get this thing called mean time to upset, as opposed to the standard mean time to failure of the time before you get a radiation-induced fault that's detectable. And various vendors claim all sorts of things, but it's hard to tell. Dramatic improvements in soft error recovery will compare to what. And if you run the thing at sea level, you're going to get a much better performance than if you run it at altitude. So they don't specify the altitude. But in any case, they're trying to fix this. They're just not very clear about how they're doing it. So the point is, this is for $1,000 server-grade CPUs and server-grade hardware in general, error-correcting RAM, and so on and so forth. Everything else isn't so seriously engineered. So you've got standard embedded CPUs, system buses, I/O devices, whatever. So, okay, you haven't got all this radiation hardening built into these things. How do you build a reliable system when you've got unreliable components? So there's a lot of work that's been done on fault-tolerant systems. The general terminology for this is X out of Y. So X out of Y units have to fail for a system failure. Standard systems are 1 out of 1. So you've got that, for example, as a process controller there. If any one of those any one of those parts fails, you get a system failure. For fail-safe systems, you've got 1 out of 2. So both systems have to fail for an inadvertent activation to occur. For high availability systems, 2 out of 2. Both systems have to fail to get an overall failure. And then you've got even more complex systems, 2 out of 3 with voting circuits and so on and so forth. The problem with these is all of these require custom, specialized, expensive hardware. So what you can do is use a variation of 1 out of 1 called 1 out of 1D. So that's a standard 1 out of 1 system, completely standard off-the-shelf system, but it's got a diagnostic channel. So it tells you we've had a fault, as opposed to standard 1 out of 1 systems, which just keep running and they're oblivious to faults. So it's basically a fail-fast system. And in the case of radiation tolerant stuff, it's pretty standard for this. You detect a fault, you restart the system. And in fact, for properly designed SCADA, so not IoT or Raspberry Pi or something, but actually properly designed SCADA devices and embedded in general, this is fairly standard. You've got a very, very fast restart. It runs directly out of flash. There's no boot process or anything like that. So you can restart the system in virtually no time at all. I know from a friend of mine, he was driving around a racetrack and he restarted the ECU as the car was traveling at 100 and something odd kilometers an hour. I mentioned this during last year's talk, and it restarted so quickly the engine didn't even miss a beat. And there's a theoretical model of this called the Swiss cheese model of failure, meaning it's a model of failure, but you can also see it as a model of failure prevention, developed by Professor James Reason, who's done a lot of work on failures in complex systems. And so the basic premise behind the Swiss cheese model is defenses are imperfect. Think of Swiss cheese. However, if you put enough layers of Swiss cheese one behind the other, eventually it will stop most failures, because to get an actual failure that goes through all those holes, every single hole has to line up exactly. So even if each individual layer is full of holes like a Swiss cheese, several layers of that are very good at stopping failures. So basically, you need to constrain the control and data flow in such a manner that error propagation throughout the whole system is pretty unlikely. So you take the Swiss cheese model and you turn it into programming practice. So you add enough layers of constraints that faults moving processing outside this permitted envelope is highly unlikely. And there's a concept called design by contract introduced by Bertrand Meyer in the 1980s. And the basic form of this is that you've got preconditions and postconditions and invariants inside every routine or function or whatever that have to hold. So it constrains it to stay within these this envelope, the safe envelope. And in C, you can do this as macros, so it's pretty straightforward to do. So here's an example of this. This is designed by contract. So as you call this function, every single parameter is checked to make sure that it is within this envelope. So it has one of the values that it's allowed to have and nothing else. And so the precondition is that input parameters are expected. And on the one hand, it's basic good sanitation. It also does things like it catches wild jumps into code. For example, if you use ROP to jump into export private key, it'll be caught because all the input parameters won't have valid values. And it's a fundamental building block for most of the later safety measures. So range checking C obviously doesn't have this standard buffer overflow. If you've got the counter there, it becomes unsigned size T, so a negative count value becomes a huge positive value, and this leads to endless security vulnerabilities. So what you do with that is you implement integer bounds checking functions for the most common cases. Again, standard C macros is integer within range. It's in the range of 0 to say 1,000. So if it's a negative value and it becomes converted to a size T, it doesn't become a large value and you get an overflow because this range check will catch it. So basically before every memcopy operation or whatever, you add this range check to say this is an integer within a valid range. You can do the same for enumerations and flags. Again, it's pretty straightforward stuff. You're just mucking around with a preprocessor and naming. So if you pass in a value that's supposed to be an enumeration that has 5 values, this guarantees it has those 5 values and nothing else. And you can also use it to deal with compiler brain damage. That's an example of an LLVM optimization. So notice there's no default at the end of this. So because of that, LLVM says, okay, we can just do it into a jump instruction. We don't have to catch anything that goes off the end of the array. So if you pass in a value that isn't in A, B, C, D, E, or E, it will jump randomly into memory. And that's the compiler behaving as the standard lets it, but probably not as the programmer would expect it to do. So again, standard, there's no bounds checking. So you need to check an index into a block of memory. And a fairly standard one is, we've got an index into a chunk of memory is the range from start to length within this array from 0 to total length. And it's also a very common exploit vector. So again, preprocessor trick. Before every operation that moves around with memory or potentially overwrites memory, you add one of these bounds check operations. Okay, loops. And this is a real biggie because you can exploit loops and you can use them to do things you're not expecting. So a standard form of a loop, count up from 1 to 10, and so it calls do stuff with the values 0 to 9. What if there's a fault? You end up calling do stuff with things like that. Now, if it follows design by contract, it's going to catch at least some of those, but it's still invalid input. The other thing is the loop will never terminate. Once it gets outside that range of 1 to 10, it will just keep running and overwriting memory and doing God knows what because it's gone outside the expected range. Okay, so you can make the loop variables unsigned and use a less than rather than an equality comparison, it means it won't at least go negative. Yes, it will eventually terminate for a simple loop. For a complex loop, it's not going to terminate. You've got all sorts of conditions there that may change the index variable, whatever it was, whatever. You can't really guarantee it's ever going to terminate if there's a fault on any of those values. And this is even worse. Will this loop terminate? Well, you have no idea. It's just going to go randomly through memory and do God knows what. It's supposed to terminate, but you can't say anything about that loop, whether it will actually ever terminate in the presence of faults. So make all loops statically bounded. You include explicit loop counters in the loops. And again, this is an example. So now it's a double indexed loop. You can hide this with macros. There's lots and lots of C macros involved. For most loops, you've got a pretty good idea what the upper bound should be. If you're expecting, 20 data items, you make that the upper bound. Very few loops are truly unbounded. Or in general, if it is, let's say, a very large loop, you can say loop up to 100,000 and then stop. And again, it's done via macros. So basically, the loop now is expressed as a macro rather than a standard for loop. And that is now a loop with loop bounds checks. Except that then the compiler screws it up. So if you do a loop like that, effectively what the macros are turning it into is that loop with 2 indexes. So the compiler recognizes that both the incrementing a value and the bound on one loop is 10, the bound loop on the other is max count. It knows that 10 is less than max count, so it rewrites it back into a standard I equals 1 to 10 loop. So now you end up fighting the compiler. The way to do this is you have variables counting in different directions. You have one counting up and the other one counting down. And so the result of that is the compiler can no longer merge the two, and it does maintain these 2 separate index variables. If you've got a loop that counts down, you do the opposite. You've got a second variable counting up instead of down. So then you've got the expanded form. I'll skip through this. I'll put the slides up afterwards if you want to see this. This is just basically to illustrate what these macros are then turning the code into. So now all loops are statically bounded, and we can guarantee termination after a fixed number of iterations. Except then the compiler comes back again and screws it up. So you think, what can the compiler possibly do with these 2 loops that will cause problems? Well, if you compile it with GCC, and O3 is similar, it's vectorized, it just makes it more complicated to understand. So that's what it actually turns that loop into. So instead of doing this nice less than comparison, it just turns it into a not equal. So it's that fault-prone loop that we had at the start, which the compiler has taken a proper bounds check loop and turned it back into one of these fault-prone loops. It's x86 ARM, it does the same thing, MIPS, PowerPC, RISC-V, Spark. So it's not architecture specific. This is universal across all GCC produced code. GCC, I've not found any version of GCC that will actually correctly compile this loop. And by correctly, I mean preserving the semantics of the original code. So what it's doing is it's converting all loops from a safe 0 to 10 or whatever index bound to an unsafe it doesn't equal equality comparison rather than less than that bound. And GCC then adds a bonus feature. If you put the bounds check within the loop to force it to do this, it says, well, this is not doing anything, so I'll throw it away. Because it knows that and again, this is a problem with compilers. The GCC knows that that value will never become negative because it assumes that this is a perfect computer working in a perfect environment. If you know that there's going to be faults, you know that value can become negative due to a fault, but GCC assumes the computer and CPU is completely perfect. So the emitter code treats the bounds checks as pointless and removes them. So you lose both loop safe and safe bound operations in one go due to compiler optimization. So, okay, what about other compilers? There's Clang, and it does the same thing. And again, so ICC actually gets it right, sort of. It doesn't unsign comparison on both, even though it's supposed to be signed. Visual C gets it wrong, or at least makes it unsafe. PowerPC is a bit special because they've got a specific counter register, so the loops don't work quite the same way. SunCC gets it right. Notice there's a signed and an unsigned branch where the C code says do a signed and an unsigned branch, so it gets it right. So basically, there exists at least one compiler running on at least one computer which will compile this code correctly. Everything else gets it wrong in the sense of rewriting the loop so that it no longer does what you want. So you're now fighting the compiler, and the way to do this is you add an invariant check in the loop body, which I'll cover later on. So, and this is not just a problem in this kind of case, it's also a problem in the real-time control world, where, for example, it's known that this compiler on this hardware will produce correct code. And so you have to compile with optimization disabled, because once you enable optimization, it destroys the one-to-one mapping of source to object code. And there's a couple of industrial control specs and safety specs that actually warn against optimizing compilers. And I think I mentioned in the automotive control systems talk where people are buying 1990s vintage PCs off eBay because they know the compiler works on that, and they can't guarantee that the compiler does the same thing on a different PC. What if we disable optimization? Well, then it works, but the resulting code is terrible. There's also a compiler called CompCert, which is a formally verified optimizing compiler. So this is formally verified. It contains a mathematical proof that the generated code will conform exactly to the semantics of the source code. And if you've ever tried to build it, it's secondary purposes. It's a mechanism for getting people to swear in French. So it does get it correct. It is a correct signed and unsigned branch. However, it's basically about the same quality of code as GCC with optimization disabled. So it's unclear whether this is a side effect of preserving the semantics or just poor code generation. But in any case, if GCC with no optimization produces the same results as the compiler, it's not terribly useful. So, okay, there's a way of fixing that and of dealing with another problem. We know we got to the end of the loop, okay, but what happens inside the loop body? If you get a fault inside the loop body, you may skip from iteration 5 to iteration 10. So the post condition's met, but the loop wasn't actually executed as intended. So in this case, for example, let's say you exit at I = 7. The iteration count is greater than 0, which means the loop check is verified. So as far as you're concerned, it's fine. There's been a fault, but you haven't detected it. So you haven't met that 1 out of 1 diagnostic criterion. And this is great for glitch attacks. So for example, typically what you do there is you glitch a password checking loop to bypass password checks. This is some sort of pseudo assembly language off some sort of random device. And basically it loads a loop counter, which is R1, and then it does a timing invariant compare. So basically it iterates through the loop the given number of times, alls the values together. So exclusive alls the values together. And at the end of that, if the result is 0, then it knows that you have that the check is passed without revealing how long the password is. So you can't break out of the loop at a certain point by putting in a fake password and check one character at a time. However, what you can do with this one, and this was popular with smart card hackers in the 90s, is you glitch the clock. So you send through two clock signals in the space of one. And what happens is the PC is a very simple piece of circuitry, so it can easily catch up. It can easily run with this double clock glitch. The ALU is a very complicated piece of circuitry, and it only executes one instruction in the space of this clock glitch. So what happens is effectively is you jump out of the loop, because the program counter does two instructions, it exits the loop, and then you've bypassed the password check. And yeah, there's things like smart card unloopers, which were designed specifically for this. So you get pay TV smart cards, you put them into these things, you glitch them, and then you get past the security checks. Today, it's more likely to be voltage or electromagnetic glitches. So you glitch the reset signal, you do brownouts, things like that. And now you can address this by using loop invariants. So if you look at this, this is the standard loop before, at least the expanded macro form of that previous loop. And if you look at this, you notice that the ratio between the two loop counters, because you've got one loop counter counting up and the other one counting down, and the ratio between those two is constant. And so you use that as your loop invariant. You make sure that that constant ratio is maintained for every step through the loop. And again, lots of horrible C macro mess that does all the job. And again, you've got reverse loops, and you've got ones where there's no fixed relationship between the two loop variables, and so on and so forth. So basically now this is our long-suffering loop. The expanded macro form is way too ugly to ever look at. But what this means is that it guarantees that this loop will always terminate, even in the presence of faults, because there's two loop indexes, one counting up, one counting down. It guarantees you can't glitch it, because if you do glitch it, then that invariant isn't met. And it guarantees once you get to the end of the loop that everything is as it should be. And also, if you've got a fixed loop that always counts to 10, you can do another check to say that, yes, I has counted up to 10. Okay, so then you've got static arrays, and these have fixed bounds, and that again makes it very, very easy. You know in advance exactly how big this thing is, so you can use a C macro and make sure you don't go off the end of the array. So in this case, all you do is you overallocate arrays by one element, and then again, horrible C macros, which I won't bother going into. But what this means is that, first of all, you know how big the array is, so you know how big to make your loop bound. Secondly, you've got the soft bound at the end of the array of the last value being null. If you don't hit that, then the hard array size bound, which is the loop bound, is triggered, and you know that there's been a fault or a glitch or something like that. That loop I mentioned earlier, where you can't guarantee termination. Okay, let's take this and make the loop itself safe. So you've got a loop with a hard bound in it. So this will terminate eventually, but we don't know where the pointers will end up going before you trigger that hard bound. So the problem with this is pointers are two valued. You've got null, which means it's not valid or not set, and you've got anything else which means it's probably valid, or at least it appears to be valid, even if it isn't. So pointers should really be tri-state. So it should be null, a valid pointer to an item, or an invalid pointer. And the way to do this is you take pointers and you turn them from vectors into scalars. So basically, you store a pointer and its complement. Or you can exclusive OR it with a mask, or do whatever you want. I mean, the easiest way is just to store the pointer and its complement. If you exclusive OR it with a random mask value, that makes it much more difficult to, if you can inject faults into that, to manipulate pointers, because you don't know what the random mask value is, and so you just end up with garbage. And then there's function pointers, which have their own problems. But basically, you just hide the whole mess behind macros. And so you've got this basic is valid pointer operation, which says, is it valid, and which is exclusive of all the two values together. You make sure it's all ones. And as I mentioned, you can mix in a random value to make malicious pointer overwrites difficult. And so now this data pointer, whatever, can return one of three values for a pointer. The pointer is null, the pointer is valid, or the pointer is not valid. And again, lots of macros for this. So now you've got a list walking loop, and it's again the get the next pointer thing is hidden by or is hidden behind macros. So you've got a bounded loop, and you've got guarantees that you've got a valid pointer that gets passed into this do thing, and you can add extra checking as required. So yeah, I'm noticing one of the questions is saying, what happens if a fault is detected? You get the situation where I mentioned earlier. So these are typically used in embedded systems and embedded devices where you fail fast. So once you detect a fault, you immediately restart the device, and it comes back from a known clean state. And it's predicated on the fact that, you know, this is not a full-size Linux system where it's going to take 5 minutes or whatever to reboot. It reboots virtually instantly. It's a fraction of a second, and it's back running again at full capacity. It's a technique called rejuvenation. I mentioned this last year in the automotive systems talk. So, and that's a standard fault mitigation technique. You basically restart from a clean state if there's a fault detected. So again, safe Booleans. Booleans are really nasty. Booleans are yes biased. You've got one single value for a 32-bit value integer. You've got one single value that's false and 4 billion values that are true. So here's some Booleans that you really don't want them to be yes biased. Access authorized, eject reactor core. You don't really want that to be yes by default. And in this case, almost any fault or malicious overwrite or anything will set a Boolean to true. And there's some examples of this where they affected hardware devices. So NXP devices, they used one of the following 4 magic values to flag security measures. So if any of those magic values were set for a flag, then security was enabled. The remaining 4 billion values meant that security was disabled. So you just needed to glitch one single bit on the security flag and it disabled all of the security. So really a Boolean should have one false value, one true value, and 4 billion values saying invalid. And again, there's some requirements there for an embedded software safety critical development guide for doing that. Now, this is one particularly for radiation. So you take various common bit fault patterns that are susceptible to bit faults in memory, and you use that as your magic value for a Boolean value 1. If you want security, on the other hand, store an unpredictable pattern. Again, you're worried about someone overwriting all of memory and setting a flag to true. So store an unpredictable pattern that's generated when the application starts. So again, the compiler strikes again. The compiler can, in theory, turn this into a comparison of 0 or not 0. And again, so you've got design by contract. So at the start of it, you require that it corresponds to that magic bit pattern of true or the magic bit pattern of false and not any of the other values. Safe integers is a bit more difficult. You've got intrinsics in some compilers. Windows has these portable int safe operations, but they're horribly ugly. So yeah, leave that. We'll leave that for now. It can be addressed, but it's through something called instrumented safety systems, but it's way too complicated to talk about here. Buffer overflow problems. Again, you allocate a buffer, you have cookies and canaries at the end, all hidden via macros. So basically, at the start and end of each buffer, you have a canary and you have this buffer check that you perform. So when you read data into the buffer, you do a check beforehand to make sure that the canaries are valid. You do whatever you want with it. You have a buffer check at the end of the operation to make sure the canaries are valued. Now, it won't catch all overwrites. So if you're going to write 1,000 bytes beyond the end of the buffer, it will not catch that, but it'll catch the standard overrun, underrun, whatever. Control flow integrity. This is another problem. If you've got a random jump into code, you want to make sure that a function was called in the way that it was supposed to be. For example, you don't want to call shutdown reactor by random, from some random fault. So you make sure that the control flows through the function in the expected manner. Apart from the obvious error control, it also makes ROP a lot harder because you can't jump into some random chunk of code because it will be detected. So to do this, there's something called Bernstein hashing, which is a way of turning ASCII strings into integer values with a low probability of collision. Again, done by the preprocessor. This is a real stress test for your compiler. So when you call a function like, for example, shutdown reactor, then you call it with an access token, which is that string shutdown reactor. So if you call that deliberately using that access token shutdown reactor, then that function knows it's been called legitimately. If you get a random jump into this code, then that token won't be present because it's just a random jump from other code and it will be detected and rejected. You can also enforce it within functions. So basically a normal way of implementing a function, you've got the expression of the control flow within that function is expressed by the code itself. But you can also hard code it into the function by putting in these control points that are checked, and to make sure that you step through each of these control points within a function to make sure that you haven't jumped into the middle of the function as part of ROP or something like that. Notorious example, go to fail. So in this case, control flow did not flow through that function because of that doubled up go to fail. It exited before it should have. So the way this works is you've got a bunch of sequence points within that function that you annotate with some sort of magic tag value. And as you pass each sequence points, it updates this value. And right at the end, you check that all of these sequence points have been passed. So you're expressing it once via the control flow through the function, and then at the end explicitly by this check saying all of these sequence points of these names have been passed. Again, it gets kind of ugly, but here's an example of how you do this using the go to fail. So you've got the SSL free buffer. You name that sequence point free buffer, ready hash, name that sequence point, and so on and so forth. At the end of that, you do the checking. So here's all the sequence points I should have passed. If you haven't passed all those sequence points, then you know you've failed. In the Apple case, the post condition wouldn't be met because the sequence points for update 3 and final were skipped. And so that check at the end would detect that you haven't flowed through this correctly, and therefore that there's a problem. This is a kind of an extreme case for crypto. So typically you have one sequence point per basic block. In this case, it's almost per line of code. So conclusion is, yes, you get faults in real-world systems. I'm particularly interested in them from the point of view of radiation, but also in control systems and any kind of embedded systems in harsh environments. You do get faults, and attackers can help these faults along by moving the environment, meaning the physical environment, outside the one that's expected, messing with voltages, messing with temperatures, that sort of thing. And they impact not just availability but security, because they can just a single bit. As I mentioned earlier, with these booleans, these yes bias booleans, a single bit separates safe from unsafe. And so the way of dealing with that is the out of D design, which admittedly requires, it's a bit of getting your head around. It requires some really weird programming, and also obviously fighting the compiler, because you can't just write the C code and assume it's going to work as you've written it. You then have to look at the compiled code and make sure the compiler isn't going to optimize it away. Okay, any questions?
Beautiful. Thank you very much. Well, I will just allow a little bit of time for our viewers to ask their questions. But before that, I have a couple of questions to ask you. One is related to that Swiss cheese model that you described.
Yep.
Would you see the application of that in the other fields other than just crypto? You're like putting multiple additional layers, and like you're thinking, okay, hopefully one of them will pick that up, pick the error up.
Yeah, it's standard defensive depth, but particularly that way of modeling faults and dealing with faults comes from safety critical systems and failure prone systems. So I've just moved it across to crypto but in crypto you more normally know it as defense in depth.
Mm-hmm.
Or in security, sorry.
Mm-hmm. So we got one question here. Is the work on a compiler which does the things like loop bound checking instead of using macro?
Not that I know of. I mean, obviously there's languages like Ada that do that. So yes, you can get it if you're prepared to use a different language, but then you have to program in Ada, which is a bit of a limited market.
Mm-hmm. Design by contract was an interesting concept you kind of talk about. I actually talk in my courses about that as well. But yeah, the stuff you mentioned, so if you have a loop, a fault may happen, and then there would be a random number or some value that will get inside that do stuff method that you declared. Has there been any thoughts on putting that contract or that invariant within the do stuff? So do stuff knows, okay, this is an invalid number that I'm getting and I shouldn't operate on. Could it be something like that?
So you mean adding invariants to other parts of the code outside of loops?
Yeah.
Yeah, I think that's actually something that a lot of people do anyway, but unfortunately in the form of asserts. So they'll put something in there saying assert this value should not be negative or should not be greater than 10,000. The downside to that, and programmers are trained to put in asserts, and a few programmers even do this, as proof that the things work. But the problem with an assert is that it's kind of useless because it's in there for debugging, but once you move it into the field where it's going to catch problems, then it's removed. So you really need the equivalent of an assert that is there all the time. And Bertrand Meyer actually designed a language called Eiffel, which had this as as an integral part of the language. Unfortunately, Eiffel never really took off. But yeah, there are specialized programming languages which have this as part of the language. And there are other languages. I'm most familiar with C because that's what's used in embedded systems. But there are ones that use asserts or assert equivalents, which are in there at runtime. But I think those invariants are in the code. But certainly, if you are coding like this, do not make them asserts. Make them something that actually throws a hard fault if you've gone out of range.
I mean, always when you show a C code, someone will ask, "What about Rust?" Have you looked into languages like that to see if they somehow would be more safer?
Well, again, Rust is safer. Which one do you adopt? And if the example I gave is Ada. I mean, Ada's had a lot of thought put into it, into making it safe and adding some of these features. but you're then in embedded systems, it's pretty much exclusively C and to a lesser extent C++, because you're supporting legacy hardware and just the environment is C. So yes, it would certainly be nice to use a different language, Ada, Rust, whatever you prefer. But you pretty much have to work with C.
Very good. We got one more question here.
Yeah, I saw that one. That's a pretty specialized question relating to safety architectures and such. It's, yeah, an SYL4 system I would expect would be extremely, not just extremely safe, but extremely secure in terms of fault detection. But you're getting into very exotic technology here, which I think would require an entire separate talk. But yes, that would be a good thing to do.
Got one more here.
Compiler directive, yes, I would love to have a compiler directive. And anyone involved with GCC or Clang listening to this, I would love to have a compiler directive or some keyword or whatever it is, an attribute applied to a loop, something like that, saying, preserve this loop semantics. Do not start removing things or rewriting the loop in a different way. So, at the moment, you can force it with macros. And it's not such a bad thing because, adding loop invariants inside the loop helps protect it against glitch attacks and other things. So you can force it with macros. There's a brute force way of doing it, but having compiler support at some point would be very, very nice if any compiler authors are listening to this.
Now, just for me to understand the attack vector you're talking about, so you kind of want to also stop the situation when you have a malicious process code running alongside with your crypto library, and you're looking out for all the possible ways that some part of the memory get overwritten, and then you want to detect that fault or that error. So you're assuming that the code that you run is in within this hostile environment, that some part of this memory or some glitches may happen, and then you can't detect the error. Is it the threat model you're looking at?
Yeah, so embedded devices are typically real-time OSs, so it's not like you've got 20 different daemons running. You've got one single blob, which is the operating system and application compiled into one thing. And then typically there's watchdog timers. So, for example, standard way of dealing with a fault is, I mentioned earlier that you've got a process that sits there and it checksums code memory. If the code is running out of RAM, it checksums all the code in RAM. If there's a fault, it goes into an endless loop. So it doesn't necessarily reset the system. It just goes into an endless loop. The watchdog detects that the system is locked up and resets the system. So it's it's fail fast. It's a very different way of fault handling than people are used to from a Linux box or, a standard desktop PC.
Well, some of the things we discussed, like fail fast, and these are all like the patterns, and is being discussed even for normal exception handling in the code, which also introduce epithet security. So we don't have any concept of immutability in those systems that you can lock in the memory and you're making sure as long as this process run, there wouldn't be any changes to that state of the program.
Well, if it's executing straight out of Flash, then it's reasonably immutable because you generally don't get faults in Flash because you need a high programming voltage, and a standard glitch or whatever isn't sufficient to reprogram the Flash. But you certainly assume that, and there's some more exotic techniques which I didn't want to get into, like the person who mentioned the SYL4 systems. You get triple modular redundant variables, so there's 3 copies of them, and you scrub them. So if there's a fault in one of them, you rewrite them from the other 2 copies. So it's majority logic decoding, but that's getting into really weird programming. So it's way too obscure for this talk. But yeah, as you get into environments where you do need that really serious level of response to faults, there are techniques for dealing with them. It just makes the development very slow, very expensive.
Has there been any research or any work explored these type of error or faults on the normal machines? I mean, not embedded systems specifically.
Not much. That's some of the figures I quoted of code faults. 2% produce security vulnerabilities. Every now and then you'll get some results, or people will say, people running servers with ECC on them will say we've got this many unrecoverable errors, but that doesn't really tell you much about what happens on a desktop PC.
Mm-hmm. So
it's also difficult to monitor. If you've got ECC then that's monitoring faults. And so you know there's been a fault. With a standard desktop PC, if it crashes, you have no idea what caused that crash. Was it a fault? Was it a software bug? Was it anything? So yeah, there is quite a shortage of data on this.
So if the fault happens currently in the PCs, then pretty much game is over, right? There's all these bypasses that you discussed.
If you've got a let's say a laptop with 8 or 16 gigs of RAM and you're using 1 gig to do something, then you've got gigabytes of memory that you can get faults all over without even noticing it. So, and again, that's another thing we simply don't have enough data on. With ECC, the hardware reports the fault to us. With anything else, you could be getting faults all over the place, but unless it's in a very critical location, you don't notice.
Yeah. One more thing, there was a hashing method you mentioned that it was like a token plus a function. What was the name of that? It's quite interesting.
Bernstein hashing. So it was done by Dan Bernstein, a cryptographer. And what it does, it's a way of hashing a ASCII text string into a 32 or 64-bit integer with a very small chance of any collisions.
Do you see application of that in some other places just to, protect the state that the program is, but just using that, or do you think just troublesome just to validate this token and going to be a lot of overhead?
Well, it's not a cryptographic hash because you're not trying to catch every single fault. That's the thing with the Swiss cheese model. Even if somehow you get past one fault check, there will be another fault check behind that one, and so you don't need a 100% secure one. With the Bernstein hashing, it is not a crypto hash. There will be collisions. I chose it because you can do it in a preprocessor is one thing, and because of that property that it's very good for hashing short text strings into integer values. That's the only reason why I chose it.
Oh, very interesting. I know that you've been in a committee review board for the LangSec, some of the workshops. Do you think anything from those guys, I don't know, introducing something in the grammar will hopefully reduce or decrease the chance of the error in some of these problems you described? Or this is just input validation?
All of it needs compiler support. That's what one of the previous questions was. You would need compiler support, and even explaining this to compiler authors, like I tried to explain to a compiler writer at one point, that turning I is less than 10 into I doesn't equal 10 is not a good idea, and it was like explaining quantum physics to a cat. It wasn't getting through. So yeah, you would need compiler support, and I don't know, it's a relatively obscure thing. I don't know how you would get compiler authors to do this when they could instead be doing cool optimizations or adding language features instead.
So we have two problems here. One is the compiler not doing the stuff that you want, those precondition and invariants that you want to introduce. At the same time, you're talking about the complexity of different languages that the humans need to be accustomed to write in. So kind of, you don't know, you prefer the compiler path rather than, or maybe you suggest a more compiler path to fix it there rather than getting someone, okay, just forget about this language, choose a different way of coding.
I don't have any magic need to use C. It's the one that's used, and you have the advantage again if you use some of these high-level languages, like with C. Once you start getting into C++, they have all these abstractions that they hide from you. With C, you know exactly what's going to be generated and whether it's going to be fault-prone. With C++, with some of these advanced features, the compiler generates a lot of stuff behind your back, and you have no idea what effect faults will have on that. So it's a high-level assembly language, and that is an advantage in terms of dealing with faults. Yeah,
there's the old argument around all the context-free grammars that some of them you can know that the grammar doesn't work, doesn't parse, but some of them may hide that away from you, but it hasn't even sorted the problem. Problems is still there. I guess what you're referring is like, okay, yeah, in C++, you theoretically do have the problem, but actually the problem still exists. It's just you don't know about it.
Yeah.
Perfect. Let me check if we have any other questions from our viewers. We don't have anything on IRC. Perhaps the last question will be for anyone who would be interested to explore this area a bit more, like in terms of errors or these cryptography issues that you describe. What would you suggest to look for?
There is, unfortunately, I wish there was a book or website or something I could direct you to. Most of this stuff is passed on by word of mouth among embedded systems people.
Oh wow.
I can't. Well, one of the reasons for motivations for doing this talk is to get all the stuff in one place. It's things that people have developed over time, or that you find in some standards documents. There is specifically for C. There's something called MISRA C, which is an automotive manufacturing guidelines for using C in a safe manner. It talks about the safe use of C rather than some of these exotic fault tolerance techniques. But I'm going to say I'd find it a good read, but people might think you're a bit strange if you say the MISRA C specification is a good read, but it's an interesting read, shall we say. But I don't know of one single place that catalogs these techniques, because it is mostly passed on by word of mouth.
Any conferences, even in the academic space, workshops? IEEE should have something, right? They have a conference for everything.
There are so there's lots of conferences on fault tolerance, but they tend to be rather academic and theoretical, whereas this stuff is all very much hands-on. Yeah, certainly there are a bunch of conferences on fault tolerance and reliability and safety and so on. So you don't want to go to a security conference. You want to do a reliability safety conference. Oh no, we're working on a book that's never going to get finished.
You're still waiting for Peter's draft book to finish, right? The engineering security.
Actually, one other thing, yeah, if anyone who's listening to this knows of more techniques for dealing with faults in this manner, I'd love to share information. I mean, the point of doing this talk was to share this. So if anyone knows of more techniques, passed on by word of mouth, then do please pass them on.
I mean, some of the ideas you described, like in terms of like design by contract, invariance, fail fast, and kind of some of those ideas you were getting into in terms of like making sure there is like a token that you check before you do the operation. This has been around in other language communities, and but they are mostly discussing about more like enterprise type programs, not really embedded systems. And the idea of the fail fast, was there just to handle these errors as early as possible. So once the invariant is not there, stop the code. But as you said, it's not like it's definitely not in the area you discussed. And I mean, this type of errors or faults that you mentioned, I couldn't even think of them. Like, can even someone really thought about this? Because in enterprise programs, you only think about the input that come from certain ways. You never think about what would be a glitch on a CPU to do to our code. They don't even write a test case for that.
And you're also running in what are essentially radiation hardened CPUs. So with enterprise systems, you do have that luxury of not really having to worry about it that much. It is more something for embedded systems with limited resources.
Very interesting. Well, if you don't have any more questions, I would like to thank you again, Peter. It was a great talk, great insight. Can we get a copy of your slides if that is available somewhere?
Sure. Yeah, I'll put them up and after the talk.
No worries. Thank you very much again. Please, everyone else, don't go anywhere. We have Joshua joined us. That's great. So we're going to run our second part of this evening session after a really short break. Thank you.
Okay, thanks.
Hello, everyone. Can everyone hear me? All right, I'd like to welcome everyone to SecTalks Ninja Night. What is SecTalks Ninja Night? So it's a place where you can put in practice your knowledge. You can have fun, you can learn, and you can mentor. And it's a capture the flag game. So there will be multiple capture flags for tonight. There will be 2 beginner ones and then a main one. I'd just like to take a second to thank our sponsors. So we have PwC, Google, Atlassian, SecDim, and Amazon Information Security. Really appreciate the sponsorship that these companies help us out with. So for the agenda today, so we're going to go through just a quick welcome and introduction to people who might not have been to a SecTalks Ninja Night before. We've already been through the solution to the previous CTF, thanks to Jordan. Then I'll quickly run through a couple of things about registration, how you can register as a player, and then how you will be able to register as a team. And then we're going to start the CTF. It'll run for approximately an hour. We'll give hints and guidance if need be. And then the CTF will end, and we'll announce the winners, who that will be the people who achieve first, who solve the prizes first. And then we'll be packing up. So what is a CTF? So it's capture the flag. It's a computer security challenge, and it's a program with an intentional weakness. So in our circumstance for today, they're 3 reverse engineering challenges. So you'll be able to go through and find the flag through reverse engineering the little bits of program that we've uploaded. And then you'll end up with a flag, which is basically just a string, and looks similar to the format of SecTalks and then within the brackets. So for player registration, if you don't already have a team, if you're not already part of a team, or you don't remember your credentials, or you want to join a new team, go ahead and use the link below, and I'll have that popping up shortly throughout the timer when the CTF kicks off as well. And yeah, just fill out the information there, and then that way I'll be able to go ahead and register you as a user, and I'll flick you an email with whoever else is on your team, so that way you can communicate with your team and go along with that. So once you have an email, it basically says, hey, we're all in this team. You can go ahead and communicate between yourselves, and then you guys can agree on a team password. And actually, this should all be done. You should be able to log in after that. And then after that, we're going to start the CTF. So as I said earlier, it's going to run for about 60 minutes. The first person to solve the challenge will be the winner. And then the winning teams are invited to present their solutions for next month, and also to create challenges for the next session. And also, yeah, if you're in a team and the challenge seems a little bit too easy, perhaps let other people kind of do the baby challenge, so that way they're also there to learn as well. So yeah, a couple of simple rules for a Ninja Night. So yeah, don't take it as competition. We're all here to learn and have fun. The CTF goes for 60 minutes. However, in this scenario, they should be available after that 60-minute timer, so you'll be able to hop on and play whenever you'd like. The hints are given out periodically and publicly. If we notice that there's no one really solving it and people are having issues, then yeah, we'll drop a hint for you as well. And experienced players, yeah, they're welcome to mentor beginning players. We're all here to learn. So yeah. And then after we finish up the 60 minutes, feel free to hang around and chat in the SecTalks Slack channel. It's always handy to kind of have conversations with new people. So if you have a question and you're wondering who you can ask, You're able to ask me. I don't have my icon there, but it's basically a little blue switch on Slack. I go by the name Oldmate. You're also able to reach out to any of these other people, and hopefully they'll be able to give you a hand. But feel free to directly message me, and I'll be able to point you in the right direction. And all right, this is just a quick slide to say thanks. So what I'll do now is anyone who I'll flash a banner that'll basically have the links that you need to use to register, and I'll make the CTF live, and we'll kick off. So use those links there, and you'll be able to access the dashboard and then also the registration, and then I'll kick off the timer, and I will start generating your teams. And if you need a hand, please reach out. Just quickly, one thing, I have made the challenges now all public. The main challenge is CTF Chicken, and then the 2 beginner challenges there are Crack Me Level 0 and Crack Me Level 1. All right. So that's it. Ninja Night's over for this month. I'll just quickly have a look and see who we had solved. I don't believe we had anyone solve the main challenge. Let me just refresh and double check. 0 solves on the main challenge, which is the CTF chicken. However, on level 1, we had K17, so congratulations, K17. I assume that means you solved the other one as well. Oh, okay, awesome. So we've had four teams solve the level 0, and then 1 team solve level 1. I will reach out to you, K17, and see if you would like to share your share how you did it and how you got the flag. And if, as always, if anyone's interested in or has a CTF they've got, feel free to reach out, and we can have it run for Ninja Night. It'd be great help, as this is all community driven. So really handy to have someone, a team, submit a CTF for the next one. But yeah, congratulations, K17. And thank you everyone for participating in this month's Ninja Night. And I hope to see you in the next one. Thanks, guys.